Okay, this is problem 5.1 out of Griffith's Electrodynamics textbook. Before I get started with this problem, if you wouldn't mind liking the video and subscribing, I'll be posting more solutions from this textbook and other common physics undergraduate textbooks. In addition, if you'd like to recommend a problem out of this textbook or another, then you can either leave a comment below or you can join my Discord, which will have a link in the description below, where you can suggest those problems. Okay, so let's get into it. Problem 5.1 says a particle of charge Q enters a region of uniform magnetic field B, that's pointing into the page. The field deflects the particle a distance d above the original line of flight, as shown in figure 5.8, which I have right here. Is the charge positive or negative? In terms of A, D, B, and Q, find the momentum of the particle. So let's start by finding if the charge of the particle is positive or negative. So what we're going to want to look at here is we're in text mode. I don't want to be in text mode. So our force is equal to Q V cross B. Okay, that's our force law. In fact, I'll just pull this up. So that's equation 5.1, Q V cross B. So that'll be important here to find the sign of Q. Now, what is V cross B? So that's just a right-hand rule. And remember that the magnetic field is pointing into the page. Let's see if I can change here. Okay. Sometimes they're denoted like this if it's going into the page. Okay. So you put your bright fingers along the direction of V, and then you want to curl it in the direction of your magnetic field. So right hand fingers in the direction of V, and then turn your right hand so that when you curl your fingers, it's pretty natural that it curls into the page. If you have it the other way, it would be kind of awkward. Now, your thumb then will point in the direction of your force. So your force then is in, I guess you'd call it the positive Y direction, basically up. And that is the direction that our charge is being accelerated in. So because that our force also points up, the direction that our charged particle Q is going, we know Q must be positive. If Q were negative, then it would be deflected downwards because we would have a change of sign. Okay, so that's the first part. Now, the next part of this problem wants to find the momentum of the particle. And this is a very common circular motion problem where your momentum is the charge Q times the magnetic field B times the radius of that circle we're going in. Okay? Well, Q and B are great, but what is R? R is our main quantity. Sorry, my dog just kind of pushed me off the bed here. The main quantity that we're interested in. So this, let's see, I'll use another color here. It's difficult because notes is difficult. Can't be easy. Sure, red. This thing, if you can imagine, I'm not going to draw it very well, but you might do something like a circle, and it'll have a certain radius. That's the radius we're interested in. So what I'm going to do is I'm just going to draw a little bit of a picture here. So if you can imagine just a portion of that arc. So that is some portion of the circle the arc length of the circle. And from the center of our circle, so this would go around it, this is a distance r. Okay, and I'm going to just drop this little line here. And this distance here is a. This is supposed to be kind of straight. Okay, let me draw this a little nicer. So we have a little arc of our circle, right? Let me draw that nicer. Okay, and then here to wherever that center is here. And then this is that distance A. Now, just as this is a distance r, it doesn't look like it because I drew this poorly. I was trying to avoid that. That also clearly must be a distance r because it's from the center of the circle to a point on our arc there. So that's also a distance r. But we're not, what we're trying to look at is this triangle here. Okay? And we need, we'll call it x, for example, for this leg of the triangle. Well, what is x? Well, if we look at our picture here, our x is the distance d. I'm sorry, x is not the distance d. D is this portion of our circle. So everything that's not x. So r then is equal to x plus d, is what I'm trying to say. Which means r minus d is equal to x, which is that side of the triangle we're interested in. Okay. Well, with Pythagorean's theorem, we know that x squared plus a squared equals big R squared. We can substitute in this new x into here. So it's r minus d squared plus a squared equals r squared. And now with pretty basic just algebra here, we can solve for r. So this we can expand. R squared minus 2rd plus d squared plus a squared equals r squared. Okay. Let's see here. I guess these r squareds cancel. I forgot we have an r here. That's what I was a little stumped at for a moment. I thought that the r's just canceled, but obviously those drop, and we have a squared plus d squared equals 2rd. Okay? Or r equals a squared plus d squared over 2 times d. Forgot about that second r. So now we can substitute this into the momentum equation, and this is just a common result from this circular motion that we get. So P equals Q B R, which we know is Q times B times a squared plus d squared over 2d. And that's your final answer. So hopefully that makes sense. If it did, please give me a like and subscribe, and I'll be posting more videos like this. Thank you.